So welcome back for the second part of our lectures on authenticity. Today we're going to focus on public key authentication. Let's see what we have for today. We're going to start talking about the birthday paradox, which, as we will see in a second, is not really a paradox, but it's a very useful way of talking about security of hash functions. It's going to give us a lower bound on the length of the output of hash functions if you want security. Then I'm going to move on RSA signatures, which are going to be the main example of public key authentication mechanisms or signatures that we're going to see in the course. We're going to see how to turn plain RSA signatures into secure signatures using the hash and sign paradigm. Then we're going to have some remarks about how to use signature schemes in practice. And finally, we're going to talk about how to protect against triple attacks, which is something that we have already mentioned many times in the last couple of videos. So let's start with the birthday paradox. So let's recall what a cryptographic hash function is. Recall that is a function that takes as input a very large input or an input of any size, possibly very large, and outputs a digest of the message, which is short. So the property of hash functions we want is that naturally we want the hash function to be easy to compute, to be fast to compute. And then what we're going to focus today is on the third property, the collision resistance. So the fact that it should be hard to find pairs, in this case x and x prime, such that the hash of x is equal to the hash of x prime. Remember that since the hash function maps possibly very large input into short outputs, these collisions not only will exist, but there will be plenty of them. If your input, for instance, was 2k bit long and output k bit, then for every output, there would be 2 to the k possible inputs, which map to the output. If the hash function is somewhat splits its input evenly over the outputs, which somewhat they do. So this is a huge number, right? For every output, there is a huge number of possible inputs, but somehow finding these pairs that hash to the same output is hard. And the reason why this is hard is because the nature of the hash function, the nature of the computation which is done inside the hash function is somehow the hash function breaks the relation between the input and output. The output is looks typically somewhat like a random string. So it's of course not random. It's a deterministic function of the input, but the output looks somewhat random and somewhat unrelated to the input, and therefore finding this collision is somewhat hard for secure hash functions like SHA-256 or SHA-3. So let's see what is the birthday paradox. The birthday paradox is the paradox that comes from a potential logical errors that you can make if I ask you the following question. What is the probability that two people in a group that take a group, what is the probability that two people in this group share the birthday? So the wrong reasoning why the name paradox is the following. What is the probability? You could start by arguing in the following way. What is the probability that I share a birthday with someone that I meet randomly on the street? Well, that's easy. There are 365 possible birthdays. Let's assume that people's birthdays are uniformly distributed. Then, my birthday is fixed. Then I meet someone on the street. They bring a number with them, which is uniformly distributed. So the probability that their birthday hits my number, it's 1 divided by the number of possible dates which there are. So it's 1 divided by 365. So far, so good. So now you might be tempted to think that if you have a group of people, then the way you would compute what is the probability that two people have the same birthday in this group of people is by taking the first person and saying, what is the probability that the first person shares a birthday with the others? And then you would take the birthday of the first person, and then you would ask, what is the probability that the second person hits my birthday? What is the probability that the third person hits my birthday, and so on? And then you multiply, so the probability that two random people share a birthday by the number of people who are in the room. And this will give you a very low number. But this is wrong for the following simple reason, that you're not only interested in what is the probability that the first person shares a birthday with someone else. You're interested in what is the probability that any two people in the group share a birthday. So therefore, you need to look at how many people there are in the room. And the number of people that there are in a group, the number of pairs that there are in a group of t people, using the notation on the slide, grows quadratically with the number of people in the room. So if you have t people in a room, the number of pairs that you can make is t times t minus 1 divided by 2, which is, if you want to be very rough, is t squared, which you want to be a little bit less rough is t squared half. If you want to be precise, it's t squared minus t divided by 2. But the important thing here to remember is the quadratic effect. So the t squared, that's really the important part. So now if you make a simplifying assumption that all the pairs are independent, they're not, since the same people appear again and again in a lot of pairs, but let's assume that every pair is just sampled at random, right? That you just have t square pairs and in each pair you sample some random birthdays and you assign it to them. Then the probability, then the number of pairs that you expect where you will find a collision, where you find the same birthday, is p times number of pairs. So this is approximately p times t squared. This means that when t is approximately 1 divided by the square root of p, then this number will approach 1, will be close to 1, and therefore you will expect to see a collision. So if you do the math, you will find out that if you have a group of 23 people, then you have roughly 50% chances that 2 people have the same birthday, which is the name of the paradox, the birthday paradox. What is that? Does this have anything to do with hash function? This has everything to do with hash functions, because if you the birthday paradox gives rise to the birthday attack, which is a completely generic attack to find collision for any hash function. So the birthday attack doesn't use any specific property of any hash function. So this is just something which is just based on the nature of hash functions. It has nothing to do with a particular hash function. So the birthday attack can be used to find a bound for the output length of the hash function, which is to have security, to have collision resistance for hash functions. So what does the birthday attack tell us for hash function? It can help us estimate what is the probability, what is the chances of finding a collision for an attacker. So let's say that an attacker wants to find a collision. So the attacker wants to find an x and a y such that h of x is equal to h of y. So an attacker can simply pick a number of random values x1 to xt and just compute the hashes of all of these values. Then the attacker can look at this list and can check whether there is any collision in this list. So we just pick a number of random values, hash them, and check whether we found a collision. Let's see if we were lucky. So how many values do I need to hash before I'm gonna expect to find a collision? So the probability that when I pick 2 random values that the hash would be the same, that I find a collision, it's 2 to the minus k, assuming 2 things. The first one is that output of the hash function is k bit, and the second one is that the hash function behaves randomly. And most hash functions can be approximated to behave randomly. So that's a fair assumption. So now I know that the probability for a random pair, the probability of a collision is 2 to the minus k. So if I hash t possible values, t random values, then I'm going to have approximately 3 square pairs, more precisely t times t minus 1 divided by 2. But roughly, I'm going to have t squares. So the number of collision I'm going to expect to find is 2 to the minus k times t squared. So probability of a collision times the number of pairs. When t approaches 2 to the k half, so square root of 2 to the k, then I'm going to find a collision with significant probability. So this tells us immediately that if I want a hash function to be collision resistant against an adversary that runs in time t, then I need the output of the hash function to be sorry, if I have an adversary that runs in times 2 to the t, then I have the output of the hash function should be approximately 2t if I want security. So said in other words, a hash function with k bit of output has at most k half bits of security, because an adversary that runs in times 2 to the k half will find a collision with significant probability. So again, this is not an attack which exploits any particular property or any particular weakness of any hash function. This is just a completely generic attack, which means that any hash function needs to have a relatively large output. So that's why hash functions, modern hash functions, have output length of 256 bits, which is longer than, for instance, when we talk about symmetric encryption, we said that the key length was about 128 bits. To achieve a similar level of security for the hash function, you need 256 bits, so the double, which is this effect of this per-day attack. Okay, so that's all we had to say about hash functions and the security of hash functions in this course. We will not look at any concrete attack on any hash function. This is something that you can study further if you want in our cryptography, in other cryptography courses. So now we'll go back to public key authentication and signature schemes, and we're going to see an example of that, so RSA signatures. So let's recall the syntax of digital signatures. A digital signature scheme as a key generation algorithm that produces a public key and a secret key, sometimes known as the verification key and the signing key. The signing key or secret key is used to sign the message and produce some signature S, which is then verified using the public key or the verification key, and these outputs are 0 or 1. Remember, signature schemes, as we have seen in the last video, are qualitatively different from symmetric key authentication schemes, MEC schemes, because they have this transferability property, this non-repudiability property. If you sign a message, anyone can verify it. If I sign a message and I send it to you, you can prove to someone else that I said what I said, and I can't repudiate what I said. So I can send you I can sign a contract, and I can send you a signed contract, and then if I don't act according to what the contract said, you can go to a judge and they can say, look, I have this signed contract, and this person has signed this contract. So let's see how to construct public key authentication. Let's see how to construct signature schemes. And the RSA function will come back and help us. So we already seen the RSA function or the RSA computations in the context of RSA encryption. So in that video, I also had something at the whiteboard where I explain a little bit of modular arithmetic, how the computation works, exactly how this value D is computed, and how to efficiently compute things like exponentiation, where the value you're raising to is very, very large. So if you want to see any of that go back and look at the video on public key encryption, where you can see some of the background. So here we're just going to quickly recall the RSA function, which in the context of signatures will have the functions somewhat will remind you of the RSA encryption functions, but somewhat with a different flavor. So also in RSA signatures, we have a public key and a secret key, which are identical to the public key and secret key of RSA encryption. So the public key is N and E, public exponent E, and the public modulo N. And the secret key is the same public modulo N and the secret exponent D. So exactly as in RSA encryption, N is the product of two large primes, P and Q, where the prime need to be large, like 2000 bits, to prevent the adversary from factoring N. If the adversary can factor N, then there is no security anymore. E is usually a small exponent, something like 3 or 2 to the k plus 1 for some small k. D is computed as a function of the prime numbers and E, and it's a large value. It's hard to guess. It's quite large. And again, D being a function of P, Q, and E, this immediately tells you that if you can factor N and find the prime factor P and Q, then it's easy to compute D, which is why factoring must be hard for RSA to be secure, which is why the prime numbers must be large as they are. And this with the vanilla version of RSA signatures, we're going to sign messages which are in the interval 0 to n-1. Again, this version of RSA signatures will be insecure, and we'll see why in a second. But so what is the intuition of RSA signatures? So the intuition of RSA signatures is that if you are, perhaps the person with the secret key can apply some function to the message, which only the person that has the secret key can apply to the message. And since only the person that, and this function, the one with the secret key can apply the function to the message, And then it should be possible, using the public key, to verify that this function had been applied to the message. Now, since there is only one person who has the secret key, who is the signer, if you can verify that this function has been applied to the message, then you will be sure that the signer actually has acted on this message. So for RSA, it turns out that the function that the signer applies to the message is equivalent to the decryption function of RSA, and that the function that the verifier does to verify that the message has been signed is essentially to encrypt the signature and to check whether you get the message back. So now, since E and D were chosen the way they were, and you can go back in the video on RSA encryption to see how this was, but essentially, since RSA decryption is correct, so since if you encrypt a message and then decrypt, or decrypt and then encrypt, the order doesn't matter, you get the same result, then RSA signatures are correct, and you can verify an RSA signature. But I would like to stress here that in general, it's not true that signing is the opposite of encryption. So it's not true in general that if you have a public key encryption scheme, that then you can construct a signature scheme by decrypting, by using the encryption function to verify the decryption function to sign. So this is just a coincidence for RSA signatures. Essentially, any technique which allows you to build public key encryption scheme also allows you to build signature schemes. So there is something known as El-Gamal encryption, and there are some El-Gamal signatures which are somewhat use the same technology. There are other public key encryption schemes based on lattices, or based on error correcting codes, or based on other number threading assumptions, which allow you to do encryption, and then using similar techniques, you can build some signature schemes. But it's not true that that signing is equal to decrypting and verifying is equal to encrypting in general. This is only true for RSA. This is like a coincidence in RSA. It's not a coincidence, it's due to the nature of the RSA function. But this is not true in general. So please don't say that signing is, in general, don't think of signing as the opposite of encrypting. This is not true in general. Okay, so, and if you can see also here, the syntax is quite different, right? So here, when we sign a message, what we're doing is that we are raising the message, sorry about that, it's raising the message to the secret exponent D and compute the signature S. And when we verify, what we do is that we compute S to the E, take modulo N, and then we check whether this is equal to M or not. So the verification here outputs a bit, 1 or 0. The verification doesn't decrypt. You don't recover the message from the signature. The input to the verification algorithm is both the message and the signature, and what you're doing is checking whether this signature is valid for this message. So verifying is not decrypting, and signing is not encrypting. Signing is applying a function to the message, which only the signer can do using the secret key, and verifying is verifying that that function has been applied, which in the RSA case means taking S, raising it to the E, and checking whether this gives you the M or not. Okay, so this is the basic version of RSA signatures, which, as the title slide says, it's insecure. Let's see why it's insecure. So here you have in the box, just to recall yourself, the public key is N and E. So this is what the adversary is given. The adversary knows the public key. And the verification algorithm, which of course anyone can run, the adversary can run having the public key, is take S, raise it to the E, take modulo N, and check whether this is equal to M or not. So now think about the following question. Can you find a way to forge a signature? What does it mean? So given the public key, you know the public key, can you find a pair MS such that M and S pass the verification test? So actually, I would invite you to pause the video here and try to think about this. Let's see if you can find an attack. Let's see if you can find a way of computing a pair M and S such that it passes the verification test. So pause the video now. I'm going to give a hint now, if you didn't pause the video yet. The hint is that the real signer would start with a message and then raising the message to the secret exponent, we compute the signature. Maybe the attacker has a way of starting with a signature and then finding the message which matches that signature. So that is the hint. After the hint, now you can pause the video again and see whether you can solve this exercise. So now I'm going to show the answer. The answer is that you can just, the adversary can just pick a random s, or any s, any value of s that the adversary likes, and then compute m to be equal to s to the e modulo n. So the adversary is not, I mean, the real signer will start with the message. The real signer starts with a message. I mean, the message might be pay 100 krona to this shop, right? And then you sign the message. The adversary instead, what it does is that it can pick a signature and then find a message which will match this signature. At this point, you should have the following objection. Wait, m is just a random message. I mean, if I can't control what the output m will be. I mean, I'm just taking s and then I'm raising it to the e, doing the model reduction m. I will not be able to control what the output m will be. So maybe the message that I'm gonna for which I'm gonna forge the signature for, it's a completely random message and it's completely useless. So you know, showing to someone that Claudio said some gibberish, it might not be very interesting. Claudio says a lot of gibberish anyway all the time. Yes, this might be an objection, but this is still a forgery. It's a forgery in the sense that you computed a signature on a message for which you didn't see the signature before. And this might be a problem. So this is a problem for security, even if it's just, even if you don't fully control what the message is. So let's see how do we solve the problem. So the way we can solve the problem is by using the hash functions which we have introduced before. So we're going to use the hash and sign paradigm, which in this case is applied to RSA. But you can, in general, do it to any signature scheme. And what you do is the following. Instead of taking the message and applying the RSA function to the message, instead of applying d to the message, you will first hash the message m, and then you would raise h to the m to the d and take modulo m n. Similarly, the verification algorithm is changed. So what the verifier will do is going to be to take the signature s, raise it to the e, and then check whether this value is the same as the hash of the message m. So this makes a very big difference compared to vanilla RSA. So let's see why. So here is where I would like to use the board. So let's do that. So you have here the set of all possible messages, and you have here the set of possible signatures. So when you use RSA, the honest party, the honest signer will take the message, and then applying D will compute some signature. What we've seen in the attack on, sorry, the marker, what we've seen in the attack on vanilla RSA is that the adversary can simply take S, raise it to the E, and find M. So the problem is that you can pick any S and find the corresponding message such that this message now and this signature are a valid pair. And they're a valid pair simply because you construct them like that, right? So let's see now how the picture changes if those are not the messages anymore, but those are the hash of the messages, and you start instead here with the messages. So now it's still, so an honest party will still start with the message, then we compute the hash, and then we'll sign using D. Now it's still true that an adversary can take S and then compute S raised to the E and find the corresponding value H of M, which corresponds to the S. But to complete the attack, now the adversary would have to find a corresponding M such that if you hash this M, you get H of M. But one of the properties we discussed of a hash function is that they are one way. So computing the function, it's easy, but going back here is hard. So it's easy to compute the hash function in the forward way, but it's hard to invert it. So therefore, now this attack has been negated, right? I can take S, I can raise S to the E, I can find what is the value that, I can find the value that if I could find some value that hashes to this value, then I would have found a forgery. But since I cannot invert this hash function, security is achieved. So now let me share the slides again. Right. So there are further advantages to the hash and sign paradigm. One of these is that, or two of them are that for efficiency reason. So similar to what we discussed in the context of public key encryption, we know that symmetric key operation like hash functions are much, much, much faster than RSA. So hashing a large message doesn't take a very long time, whereas computing a signature on a very long message, if you had to do it on the value itself, would take a very long time. So using the hash function, you can take a very large file, megabyte, gigabytes, hash it down, and then sign. So hash it down using a very fast algorithm, the hash function, and then signing using the slower algorithm, the signing algorithm, which overall gives you better performances. And also gives you the advantage that the signature is of fixed length. So the signature is you only have to sign one short value, regardless of the length of the message. And this means that you can sign messages of arbitrary length with a single exponentiation, and where the signature is of fixed length for any length of the message. So those are some other efficiency advantages of hash and sign signatures. But really, the main reason why we introduce here the hash function is because the other version is insecure because of the attack we just see. So let's go forward. What are some other things that you need to worry about when using digital signatures in practice? So the first thing, which the book has in bold, this is a quote from the book, which is very, very important, which might seem a trivial statement, but it's very important. It is that a digital signature commits the signer to exactly what was signed and nothing else. And this is very important because when you use digital signatures in an application, you might have the choice of choosing what is that exactly should be signed. So think of an example of using digital signatures in emails. What is it exactly that you want to sign? Do you want to sign the content of the email? Should you sign the date? Should you sign the from field? Should you sign the to field? Should you sign the subject? Anything that you sign, the sender commits to. I mean, the verifier will be able to prove to anyone else, and the verifier will be convinced that this information really comes from the sender. Anything you don't sign can be replaced by an attacker. So assume you have an application for email in which you send me an email in which you copy paste a signed message. Then someone could eavesdrop your email and then send me the same content of the email, but maybe changing the subject or maybe changing the from field or the to field or things like that. So this is really important to think of when you use digital signatures in a more complex application. Another example, which I also invited to reflect it in the book, is what happens when you sign a ciphertext. So if I receive a signed ciphertext, can I be sure that the sender knows the content of this ciphertext? And again, the answer is no, because if you send me a signed ciphertext, I know that you have seen the ciphertext because you have signed the ciphertext, you approve of this ciphertext, but it's unclear to me. It should be unclear to me whether you know the content of the ciphertext or not. You might have taken the ciphertext from someone else and then just sign it. So exactly how to combine digital signatures and encryption, it's an interesting question that you're invited to reflect on in the book. Other questions that you might ask when using digital signatures in practice is, what do we do if the keys are lost? And the book talks about what to do in these cases, but essentially you can't use digital signatures in practice without a mechanism for users to be allowed to say, my key was lost, my key was stolen, someone hacked into my computer, the key is gone. Please don't trust any more digital signatures that come from this key. Then another question you should ask is, who should keep the key? And indeed, there are very different. There's a lot of difference in between different applications. So I think most of you have experience with digital signatures in practice, since in Denmark we have a national digital signature scheme, which is connected to the NemID system. And this is an example in which you don't control your secret key. The secret key is stored for you. At least the default behavior is that the secret key is stored for you in a secure server, and you can access your secret key using your NemID interface, which means, of course, that the people who are storing your secret key have the, at least theoretical, potential of signing messages on your behalf, which might be something that is that you might find undesirable. But in the context of NemID, it has been concluded when this was introduced some years back that this was a better trade-off for the security of the ordinary citizens than keeping the secret key on their laptop, because the chances that the service provider in this case gets corrupted and signs messages on your behalf is much, much less than this risk that your own computer gets hacked and the secret key gets stolen from your laptop. Especially when we're considering the ordinary average citizen using the system, and maybe not, computer experts. And also, in the case of a system like NemID, there is a huge legal framework around this, which talks about what happens if the secret key is stolen, or what happens if the secret key has been revoked. And there is a way of turning your keys of renewing keys, of saying these keys are expired, let's get a new key. There are legal agreements that say what happens if something goes wrong, and so on. This is the same in the banking world. This is very different in other contexts, like the context of cryptocurrencies, where digital signatures are used to transfer funds. So there are all these stories there are all these entertaining stories of people who have, for instance, whose laptop has stopped working, whose hard disk has stopped working, who lost the secret key, which was connected to their Bitcoin addresses, which therefore completely lost their money, lost hundreds of thousands of dollars in a split second, in a moment where the hard disk broke. Or examples of people who have stolen money by being able to compute, to extract secret keys of users in different ways, and therefore being able to steal their money. In the context of something like Bitcoin, where the code is law, there is really no way of doing anything about this. I mean, if someone steals a secret key, your money is gone. In the context, in more traditional application of digital signatures, there are safeguards and legal agreements around the use of digital signatures. So it makes a lot of difference where you use digital signatures. Finally, something that we talked a lot about, both in the last lecture, in the context of the definition of both public key authentication and secret key authentication, is that the definition of security for both MACs and signatures, for both secret key authentication and digital signature and public key authentication, does not protect against replay attacks. So if you send me a message that say, please pay 100 krona. If you send a message to the bank that says, please pay 100 krona to Claudio, and I can intercept this message, I could keep sending this message over and over again to the bank. And the bank would simply have no way of knowing whether you signed the message 100 times or whether it is me that is doing a replay attack. As is shown here in the picture, the adversary here doesn't need to know anything. Even in the case of secret key authentication, Alice here has the key, Bob has the key. The adversary intercepts a message with a valid code or with a valid signature, and the adversary can keep replaying the same message over and over again. If the verification algorithm says yes the first time, it will keep saying yes for every other verification. So how do we get around replay attacks? Well, there are several solutions to this problem, and none of them is perfect. So it's really up to you and up to which application you are implementing and what is the best solution to be used. So the first solution is to make sure that the messages are unique. So if for some reasons you can be sure that every message is only signed once or marked once in your application, well, then you can avoid replay attacks simply by discarding messages which are repeated. So this might be because your application only sends unique messages, which might be a strange application that does that. But another way of making your application only sending unique messages is by adding counters. So for instance, your application could send one concatenated message one concatenated with the content of the message, and then message two concatenated with the content of the message, and so on. And now on the receiver side, you will check whether you have seen this message before. So this, of course, puts a burden on the receiver side. The receiver has to keep track of these counters. And this might create some problems because, I mean, the receiver has to either keep a counter which is synchronized with the counter of the sender, and then you have to worry about what happens if some message is skipped, maybe because of network errors so you need to worry about what would what does the receiver have to do if a message is skipped? What does the receiver has to do if the message don't arrive in the right order? There are many considerations you have to worry about. Another solution instead of counters is to use timestamps. This also makes the message unique, but instead of using counters, you can use time. So every time you send a message, you also send the time together with it. Let's assume that you send the time which is so precise that you never send more than a message with the same time. So maybe your time precision goes down to milliseconds, and you never send more than a message per millisecond. So this again puts a burden on the verifier. The verifier needs to have a clock which is synchronized well enough with the one of the sender. And then, of course, there might be some delay on the channel, or there might be some partial desynchronization between the clocks, which means that the verifier has to allow for some tolerance in this when verifying the messages, and saying, that I'm going to accept every message which has a timestamp which is, between the current time plus minus X%, or a few minutes or a few seconds. And of course, the larger you make this window, the more susceptible you make yourself to attacks. The smaller you make this window, the higher the chances are that you might get in trouble just because of known malicious attacks, right? Some errors or some delays or things like that. The final solution that you could use to prevent random challenges, to prevent dribble attacks, is the use of random challenges. So when using random challenges, what you would do is that the following. So let's see, it's a slide for this. So in this context, the context of using interaction, what you can do is the following. So now Alice would tell Bob, hey, I would like to send you a message, which is, or maybe Bob knows that he has to receive a message from Alice for some reason. So now here Bob picks a random number, let's call it R, and sends it to Alice. Now Alice makes the message together with with this random number R, using the key, and sends this back to Bob. So here Bob can verify that this message was really sent by Alice. Not only it was sent by Alice, but it was fresh. What does it mean fresh here? It was the reply to this particular random challenge which was just sent. And here the point is that the next time Bob wants to receive a message from Alice, he's going to send a new random challenge. And yet the adversary can't send back the old code, the old signature, because if the adversary did that, these values will not be valid anymore for this new random challenge. And the adversary not having the key cannot compute a new valid code or signature for this particular random challenge. So this is somehow a solution that you might have seen in a slightly different flavor in other applications in which you get a random challenge from a website, which then you have to input again to demonstrate that you are fresh and that you are alive and that you're actually interacting with the protocol, and there isn't some kind of man-in-the-middle attack going on. So also in this case, interaction and the usage of random numbers is useful in a different context. So again, Bob sends a random number R, and Bob rejects if he receives a message with the wrong random R. So of course, also the solution puts some burden on the receiver. Here, Bob needs to store this to remember R at least until the connection is over, And maybe if Bob is keeping a lot of different connections, he needs to remember which R's correspond to which connections and things like that. So this also puts a burden on the receiver.